We are going to see these two methods. First one is Parzen method, and the second one is k nearest neighbor estimation. So these two methods, they estimate probability of x given omega j. So once you know this, use base to find out probability of omega say j given x. So this becomes usual problem, but first of all we need to estimate this thing. So this is one way. The second or third rather is called as k nearest neighbor classification, where we estimate directly from data probability of omega j given x. Okay, and these methods are quite popular till now, where we do this estimation directly from data. Okay, so we will move slowly from the first two methods, then we will see what is the third method, which is, as I said, very popular. So in earlier study, we assumed that the form of underlying densities are well known to us and we estimate their parameters only. So parameters are calculated from data. So that is called as parametric method. Now, for example, suppose I take multi-modal density. That means there are many peaks in my data. Suppose unimodal means I take a normal distribution curve where there is only single peak. Okay, and suppose I have data distribution something like this. So there are say two peaks, say one is here and another other is here. I may have third here also. So if there are multiple peaks in my data distribution, then assuming a normal distribution that is only single peak on this is not a good idea. So I hope you got this point. If my actual distribution is like this, and if I assume that this data is distributed like this, so this will be a wrong assumption. I should not fit rather this kind of curve for such kind of distribution. Okay, so this is, remember this is probability of x given some omega. Okay, and this side is your variable x. So non-parametric methods can be used with arbitrary distribution and without the assumption that the forms of underlying densities are known. So you can have any kind of shape. Suppose I have this shape as my distribution. So there is no regular shape here. So this is, if this is my actual data, then I should be able to fit or find out this probability of x given omega very easily if I go with non-parametric method. You can have any shape, maybe some triangular here, then like this. So all these kind of shapes are possible. So there are several types of non-parametric method. Two of them are of our interest, that is estimating the density probability of x given omega j, and the second one is estimating directly posterior probability, that is probability omega j given x. Now uh, need to estimate the density or likelihood of each category at the test point x. That means suppose I am given some, let us, I take some other point. Say this is my X point. I want to classify this. Okay. I want to classify this. Then what I can do is I can take some area around it. Okay. And then I try to compute probability of X over here. So how do I do it? I take the number of samples in this small area. Say there are k such samples out of total number of n samples. So in my problem domain, there are total n samples. Out of that, k samples do fall into this small domain. Then I divide this by the volume. So if I divide this by volume of this particular area, in this case, it will be the area of the circle. But you can imagine if it is multidimensional, then it will be a volume. So this will be the density of the probability at this location. Now the probability P that a vector X falls in region R. So be careful now what I am deriving. The probability P that a vector X falls in a region R is now probability equal to integration over the region, this probability density function integrated over this region of interest. Okay, so p small p x dash is some variable uh, which runs over this region, and I am just integrating over that region. Say this is my region, so my integration will run for all this region, and we are taking x dash as our variable. So if I take this small portion and do the integration, so whatever integration is of the density is my probability. So if we have a sample of size n, the probability that k of them fall in R, that in region of interest, is given by the binomial law. So like this, so I can call this as maybe equation 3. So this is pk equal to, I should say, nck into probability p to the power k1 minus p to the power n minus k. So this, this is the binomial law, and the average value or expected value for k is np. So for the average or mean value for binomial distribution is np. So for the mean value k, that is k is equal to np. So this p is equal to k by n. So as we expected, the ratio k by n is a good estimate for the probability p, and hence p of x. So when n is of large value, say maybe 1000, 2000, or maybe 10,000, so as this n number of samples are quite good, then this estimation is better and better. So assume p of x is a continuous and that the region R is so small that p of x does not vary significantly within it. We can write the earlier equation number 1 by bringing out this p of x out from this integration, that I assume now this as constant for a small region. Then this is my volume simply. Okay, so finally we get the same equation we started with. We start with some intuition. Now we can see that this intuition is a good approximation of probability of x. So this density. So this is density estimation. So density estimation at given point x is equal to k, that is number of samples falling in this region. So k divided by total number of samples in my problem, that is n, and divided by volume of this region of interest. But there are several problems that arise when we try to estimate k by n by v. Now, what is my estimation? Remember, is I need to compute k by n by v. Okay, so practically, if we fix volume and take more samples or increase n, we get a space averaged value of px. If that means if I keep on increasing number of samples and fix the volume, say this region is fixed, and if I keep on taking more samples in my problem domain, then this estimation p of x will be the average value of actual p of x. Okay, I can say estimation p of x will be average of actual p of x. So therefore, to obtain p of x, we must shrink the volume. So to have a better estimation, what I mean, if I take the one-dimensional case, suppose this is actual curve and I fix the volume like this, then the estimation here p of x is the average of this curve. Okay, so average of that curve within that domain. Just 1 second. Okay, so if we fix this volume, then there will be some averaging effect in prediction of this or estimation of this probability density P of x. Now, however, if we fix n and allow v to shrink to 0, we may get probability of x equal to 0. That means if I keep on reducing the volume, if this is a 1D case and if this volume is uh, reduced, then there may be a chance that nobody is falling into this bin. Okay, if nobody falls into that, that means k becomes 0, then there won't be any probability. So that will be 0 by n by v. So everything is 0 then. So that is also not desired. Okay, so the keeping value of this window size is very critical, and that will hamper the calculations. This is the key point that one should note while using this density estimation methods. So practically we cannot be allowed to become arbitrarily small, and we must accept that whatever we obtain has some variance in it, and there is some sort of averaging effect. Okay, so whatever we estimate is not actual value. So if this is my actual value, and this will be the estimated will be approximation of this actual value. So this px tilde is the estimation. So that will not be equal to the actual distribution p of x, but it will be some kind of approximation near to that. Okay, so still it is fine because it works very well. So theoretically, what we can do is if I take some small region R1, and suppose we form a sequence of regions R1, R2 with one sample in R1 and two samples in R2, three samples in R3, and so on, then n samples in Rn. If Vn is the volume of Rn, that is the region, nth region, and Kn is the number of samples falling in this Rn. So I took some region called Rn. There are Kn samples in that, and volume is Vn. Okay. So the estimation or estimate of P of x is Pnx equal to Kn by V. So that we have seen already. And if Pnx is to be converged to P of x, that means to make P, what I mean is Pnx is the estimation. If you want that this should be equal to the actual distribution, then what we have to do? Then we have to have these three conditions that one should satisfy. This limit of n tending to infinity, then Vn should shrink to 0. That means if you have infinite number of samples, then volume should tend towards 0. Doing so, one must have this Kn equal to infinite, limit n tends to infinity, and Kn by n, this ratio should reach 0 when n tends to infinity. So there are some contradictory conditions that are appearing in this situation. Meaning of this is that the first condition assures us that space average P by V will converge to Pfx. So this is required condition when you want to have the estimation equal to the real density. Now second condition assures us that the frequency ratio k by n will converge to the probability p. So I should have sufficient value of Kn in my bin. Okay, and ideally I should have such infinite samples, but this Kn should not be, or rather it is a part of number of samples n. So n is also infinity and Kn is also infinity. That is practically not possible, but theoretically it means that Kn is very large and is part of the total number of samples, and these samples are also very large. Okay, so that this ratio is 0. So there are some contradictions theoretically, but thing is that whatever we do the estimation, this estimation is the approximation of the original. That thing you should keep in mind when I use non-parametric methods. So this is the way of approximating it, not the real computation. Now there are two ways to obtain the sequences of regions that satisfy these conditions. The one method is called as Parzen window method, which is called as shrinking region method. And the other one is called as k nearest neighbor method, which is growing window method. So all these methods are window methods. So what I mean by that we will see in next slide. Now shrinking window is where this volume Vn, we assume it to be 1 by square root of n. So that means if you have 100 samples, then square root of 100, that is 1 by 10. So volume you assume to be equal to 0.1. Okay. Now the other way is growing window, where we assume that k is equal to square root of n. That means we will count or we will grow the window till we get this count kn equal to root n. Say there are 100 samples, then we are in search of root 100, that is 10 samples. Okay, so we will increase this window till 10 samples are falling into this. Okay, in this Parzen window, we fix the window size equal to, or the volume equal to 1 by root n, and see how many samples do fall into this. Okay, so as n grows, this volume will shrink. Okay, so that's why it is called as shrinking window. And here, as in the case of k nearest neighbor, as n increases, the window size also increases. So this is called as growing window. Now this is one example where we have comparison between the two. Now suppose here this is Parzen window, and I have only n equal to 1, then n equal to 4, then this number of samples, n equal to 9, n equal to 16, and n equal to 100. So if I use Parzen window, the volume size, it will be 1 by 1, that is 1 if I have only one sample. Now if I put n equal to 4, so if I put here 4, so it will be 1 by square root 4, that is 1 by 2, so 0.5. Okay, so you can see this volume is shrinking, and it's reducing when I use further n equal to 9, then n equal to 16, and then n equal to 100. Now here in second case, k equal to root n, you can see as the number of samples are increasing, the k, that is number of samples falling in this particular window, that is circular window, is increasing. For example, suppose I put n equal to 1, so this kn is equal to 1. So I need to grow this volume such that k is equal to 1 will appear. Okay, that means number of samples within that volume will be equal to 1. Now if I put n equal to 4, that means kn equal to square root of 4, that is 2. So I am in search of two samples. So here you can see there are two samples. I should use or grow this window such that two samples are incorporated. So sorry for the interruption, but I need to stop because of the urgent meeting for this pandemic. As you know that we are shutting down the institute from tomorrow. So from tomorrow, the actual institution is closed. We have to work from home. So there is one urgent meeting. So we will see the next part uh, in next class on Monday. Okay, so thank you. So let us stop here.